Hello, good afternoon, everybody. We're happy that you're here. Hopefully you have still some energy for this session because it has already been a long day, but we're very pleased to meet you here. My name is Greet Ruysgaard. I work at ILVO and I'm the coordinator of the MARVIC project, and I am co-chairing this session together with Marta from GMF. And she is the coordinator of the MRV for SOC projects. And the both projects are actually two soil mission projects, which were funded in 2023. So we are already working for more than 2.5 years. So we thought it's a good time to present some results from the projects, actually. So the projects were funded in support of the whole CRCF and particularly to develop MRV systems in line with this CRCF. So in the course of the past years, we have also been in close contact with the policymakers, giving advice, and also interacting with them. So today we will have 4 main presentations about 4 case studies, actually. So 2 from each project. So have a good time. Maybe just to say, sorry, I forgot about that. So we will start actually with an introduction of the MRV for SOC project together with 2 case studies from that project. And then we will move on with 2 case studies from MARVIC.
Thank you very much, Gret. Without further ado, MRV for SOC is mainly aimed at designing a cost-effective, transparent, and robust Tier 3 approach to measure as many carbon pools as possible in different ecosystems and the traditional management practices and carbon farming conditions. To do so, we have identified 15 demonstration sites located in 9 land use land cover classes, which are located in 5 European countries, in Spain, Italy, Czech Republic, Belgium, Germany, and 1 associated country in Norway. The implementation of the project follows this approach based on 15 demonstration sites to identify key parameters and processes that should be taken into account for the scalability of the analysis and the methodology. And we have used different process-based models because there is not one-size solution fits all. And everything has been implemented within the national greenhouse gas inventories and the CRCF regulation and the objectives to develop this MRV system for the European Union land sector. One of the things that we have heard these days is how to achieve a robust, transparent methodology, but one important part of it is to be cost effective. And to do that, we need to identify key parameters and processes that are captured by our process-based models. To do so, we have identified key in situ and remote sensing indicators to understand if remote sensing could play a key role in scaling up this methodology at larger areas where we do not have a dense network of in situ measurements. To do so, we have identified mainly soil properties, vegetation properties, climate properties that could be substituted with remote sensing indicators and characterize the quality of input data through different error metrics. One of the relevant conclusions that you are going to see in the following presentations are related to the identification of those relevant in situ parameters so that we can reduce the cost of implementation while maintaining the reliability and robustness of the approach. It's also very important to consider the model initialization, the parametrization, and the representation, as I was saying, of these key ecological processes so that we are not investing in developing very complex and comprehensive tools that are not measuring what we want to measure and those covariates that can capture the largest variability of the model. And then the characterization, as was mentioned before, of these errors play an important role in establishing this transparent MRV framework and build trustworthy collaborations and solutions and get the engagements of different stakeholders across the value chains. And then finally, we have the comparison of different simulations based on single-site and multi-site calibration. This is ongoing work to improve the scalability of the model and the uncertainty estimation. So without further ado, I would like to pass the floor, if I can change the slide. Can you please help? Yes, of course. I would like to say thank you on behalf of the whole consortium of our 20 partners and one affiliated entity. And now you will see this concept into action with the next presentation delivered by Judith Torres from CSIC.
Thank you, Marta. So as Marta has just said, I'm going to present our results in one of the MRV4 SOC demo sites, the Brainfoot serial demo site in Spain, and how we have been dealing with the ROTC parameterization in Mediterranean conditions. So our case study is a long-term experiment, La Canaleja, which is a rain-fed cereal system and is located in Madrid, and it has Mediterranean semi-arid conditions. From this long-term experiment, we have selected a time frame of the second phase of this long-term experiment, which is from the 2006 until 2021. And we have selected two tillage intensities from the three that they are experimenting, which are conventional tillage and non-tillage. And we have also selected two cropping systems, the wheat monoculture and the 4-year rotation. So of the total of the 60 plots, we have selected 16 for this project. So in total, we have 4 treatments: conventional tillage monoculture, non-tillage monoculture, conventional tillage rotation, and non-tillage rotation. In the whole 16 plots, we have been measured the soil organic carbon through almost all the years in the time frame of the study. So we have experimental results of the SOC measured in the field. And as you can see in these graphics on the left, here we have the soil organic carbon stock in the different, at different depths, and also in each of the treatments. In green, you can see the non-tillage, and in blue, you can see the conventional tillage. And as we can see here, in the first slide, in the first graphic, from 0 to 7.5 centimeters of the soil, we have the strongest signal of the separation between conventional tillage and non-tillage. Then in the next depth, from 7.5 to 15 centimeters, this signal is weaker, and then from 15 to 30 centimeters, it disappears. And when we aggregate the SOC stock from 0 to 30 centimeters, we find that this separation in the treatments, it is also weaker. And once we have analyzed the results, our experimental results, we have tried to parameterize ROTC to achieve the same results in SOC as we have seen in the field. So as you may know, ROTC is a model based on the turnover of organic carbon in soil, and it works with the decomposition of organic matter into 4 active compartments at different decomposition rates and a small amount of inert organic matter. And we have, ROTC have some data requirements, for example, temperature, precipitation, evapotranspiration, also soil data, like clay, initial SOC, and carbon inputs. Our carbon inputs are calculated based on the biomass from crops and also on the biomass from weeds in the fallow of our rotations. Then we have initialized the model with a spin-out procedures using the average of the first 4 years of our baseline treatment, which is conventional tillage monoculture. We have conducted this analysis in soil air package of Air Studio. Process-based models are good proxies to estimate soil organic carbon, but they need to be properly parameterized. One of the parameters that can be changed is the tillage rate modifier, which is a modifier that, it acts on the composition based on the tillage. So we have in the literature you can find that for conventional tillage this TRM is 1, and for non-tillage is 0.95. But for Mediterranean conditions, this is not so clear. And we have conducted some analysis to see which are the best TRM that we can use in our conditions. And for this, we have implemented the soil respiration rate from experimental data in La Canaleja. And we have done bootstrapping with 10,000 iterations, and we have an average TNR of approximately 0.7, which is also a value that is found in some reference regarding Mediterranean conditions from other authors. So our first results are those, and you can see that we have achieved a good trend, a good direction and trend of the soil organic carbon, with the non-tillage rotation in green, dark green, as you can see, as the highest treatment. But we have very low values of soil organic carbon in the simulated results. So we need to parameterize better our model. And for that, what we did was three adaptations. First, we changed the soil moisture limitation, which for ROTC it has a moisture modifier which reach a limit of 0.2 for working in a more wet conditions. When we are in a drier conditions, Farina and her colleagues have developed a modifier that reaches a lower value of 0.1, which allows less decomposition, and it's more adapted to dry Mediterranean summers. So we have also implemented this, and also we have implemented a seasonal and management soil cover factor. ROTC includes a plant cover factor that slows the composition when soil is protected by vegetation or residues. And we have implemented it monthly for the crop cover, the bare soil, non-tillage, and the fallow. And then we have also adjust the quality of the carbon input using this crop-specific DPM RPM ratio of the composition. For cereals, we have used the one that is in the literature, but for legumes, which are more labile, we have assumed a higher DPM with faster early turnover. And now we have better results, as you can see here. Now, for the validation of our last results, you can see here in the graphic in orange, the soil organic carbon measurements in the field, and in blue, the simulated ones. The metrics shows that we have a negative relative mean bias of 9%, which means that the model underestimates our soil organic carbon. Because we have measurements repeated over time, we have conducted mixed models with with an adjustment for the temporal autocorrelation. And for these two mixed models, we have a slope higher than 1, which means that stock measurements has a higher variability than the simulated ones. So ROTC at this level can have a good trend, can achieve the trend and the direction, but it underestimates the soil organic carbon measured in the field. Then we have conducted analysis also for the delta stock, and we have used the change in the soil organic carbon between rotations. We have firstly, we used single rotations, but the metrics didn't went well. So we decided to aggregate 2 of those rotations. So, and the final results went better, especially in the second period from 2014 to 2021. Where we have a high correlation, but still a very, very low bias. And then we tried to validate each of the treatments separately, and we couldn't do that. We didn't achieve good metrics for those. And the main reasons are that we have a low sample size per year in treatment and also a high field variability. So the metrics are not good. And also it is important to take into consideration that we have a signal dissolution with depth. From the 0 to 30 centimeters, the separation between conventional tillage and non-tillage is reduced. So the conclusion so far is that, as I just said, that the 0 to 30 centimeters stock aggregation in ROTC dilutes the effect of non-tillage, as it is experimentally more apparent in the first 7.5 and even in the first 15 centimeters. ROTC must be reparametrized considering Mediterranean specificities. In our case, it is very important to consider with biomass in fallow and also a specific tier M moisture modifier and a proper estimation of soil cover factor. It is also important to have a proper spin-up adjusted to the baseline conditions. But we have found that both experimental data and ROTC outputs concur in that the non-tillage rotation is the crop management with the largest stock increment relative to conventional tillage monoculture. However, ROTC underestimates stock outputs by approximately 9%. And well, our further efforts will be to force a little more tier M beyond experimental and literature values and to change this DPM RPM ratio in non-tillage treatments and see if we can achieve better metrics in the validation. Thank you.
Thank you very much, Judith. We have decided to have all questions at the end, but we may have time for 1 or 2. So.
a little bit, and this is on me because I'm a fool, a little bit confused by the theory you had on why the ROTC and the observations, well, the potential explanation on it, because you were, one of the reasons, well, the three reasons you gave, one of them was the sampling size, but you wouldn't expect that to explain a bias. But then you had that because you have the lower level, which it, based on your measurements, doesn't change that much, respond to that much to the top level. But you, if I understood it correctly, you generally had the measurements overestimated. So the measurements were higher values than the values at the bottom. So the model projection. So the model was underestimating on average. And I was kind of curious because if your potential theory on it, and this is a genuine question, this isn't meant to stuff like that. So if your theory on it is that the reason explaining is that the method doesn't get to the bottom, I would almost expect that to lead that you had an underestimating, because if you had something that was enriching the carbon in the soil on the top, but like your model is seeing this as continuous layer, that then because it doesn't get there, that it results to you underestimating it. So why did you assume that the layering is one of the reasons behind, like in this situation, why to you is the layering a reason why the model is underestimating the measurements?
Well, more than the reason that the model is underestimating the soil organic carbon measurements, we think that this is the thing that we have the strongest separation between the tillage and non-tillage treatments in the first 7.5 centimeters. And then this is the reason that maybe we cannot find this separation even in our simulation, because the treatment that behaves like in the field is non-tillage rotation, but we cannot see in our simulations, if we disaggregate in treatments, we cannot see this separation between conventional tillage and non-tillage, and we think that it could be probably because the strongest signal of separation is in the first 7.5 centimeters of the soil. But I can. Okay, we can accept. Suggestions. Probably you can have some idea on why this is happening. Probably what is the bad metrics of the not so good metrics are probably because of the low end. I mean, we have samples.
I mean, it's still interesting work.
Okay.
Thank you very much. There is another one. If not, we'll pass the floor to Maria Fantapié from CREA. She will show the second case study from MRV for SOC.
Okay, sorry. Thanks a lot for being here, so many. Again, we are presenting our demo sites on maize cultivation. So it's the same kind of crop, but now it's located in central Italy, and it is in a mountain region. So it is Mediterranean, but mountainous climatic region. And I want to include in this slide the main contributor to this activity, which do not belongs only to CREA, which I belong to. Okay, so it's important also to say that we, as MRV for SOC, we want to also localize the demo sites in pedo landscapes. So we have done this for all the demo sites so that the results of this activity could also be used for benchmarking activities. So in the case of this demo site, it is located, as you can see in the square, in central Italy, in the mountainous region. So it is Mediterranean, but is also mountainous, so it's not so dry as the previous one. And we have also the description of the typical soils that are there, so this kind of data could be possibly used in the used also in other similar place for Italy. Okay, so this is also a long-term experiment, which was started in 1974. It has 24 plots with mice cultivation, which is also rain-fed. We have different management tillage treatments and also a continuous mice or rotational mice. You can see here all the different combination of this kind of different management systems. We didn't use all the data for all the combinations. So we were concentrating, because the problem there is that not for all the treatments we had good quality data, so we used the ones that were more continuous and usable. And so we use the data for deep ploughing in rotation, deep ploughing with continuous mice, disc harrowing, which is considered as a minimum tillage, with rotational mice, and disc harrowing with continuous mice. This is the in situ data that we collected, and so you see a lot of information that we collected for these different plots. And we have elaborated the so-called boundary conditions that were presented by Marta. So we upscaled this information through remote sensing to the landscape around. And so then we assimilated in this sensitivity analysis these upscaled maps to the modeling, so substituting to the in situ data. This just to say that we also use ROTC. I will not enter into detail. I think that people here know what it is, ROTC. And so these are the data. As you can see, we have data running from, although the long-term experiment is from 1972, but the data actually start from 1999. And so what it is interesting here is that we can have two different baselines. So one which is related to a condition in which you have rotational mice and conventional tillage. And you can compare both the rotation against the monoculture, or you can compare a rotational mice, which actually in the current practice of common agricultural policy is required, so it's no more a baseline to have continuous mice. So now the baseline actually is the rotational mice. So what it is now possible to improve is to act on tillage. So for us, the main, what we were comparing was in a rotational mice, the difference between deep ploughing or disc harrowing. And we have verified that apart from what it is the change, that it is due to climate change, so what it is the baseline, there is yet an improvement, so a stocking of organic carbon in the disc harrowing. So we have demonstrated that in this time period, there has been an accumulation actually of carbon stock, and we have measured that it amounts to 0.38 ton per hectare per year in the field measurement that was simulated with ROTC, quite similar value, that it is 0.3 ton per hectare. And this is actually the simulation with ROTC. You can see that, so the spot are the measured value, and the arrows are the simulations. Not all the spots are really, I mean, in line with the simulation. So for some, there is a higher error. But generally speaking, the simulation are quite good, so they went quite well. So we could also see that we can use, in this case, ROTC to simulate what we have measured in the fields. And then going to the upscaling, this is quite complicated slide, I can imagine to see, but it's just to show you that we were substituting for all the different simulation. First, the climate data that was derived by Terra Climate. Then we substituted the simulation done for soil properties, both for texture and for soil organic carbon. And then we also substitute the input, so the biomass input that could be simulated by remote sensing. And then we used all data that was not in situ, but all by remote sensing, just to test if a complete MRV system could run, actually, not using in situ data. Just to enter to some details, this is just to show you that in all this, you can add errors. So you have an error in the simulation itself, as you have seen. So the simulation is not perfectly aligned with the measured data. But if you apply some remote sensing or some mapping, you include the error that it is inside this. So what we have done for soil maps is this. So we produce bare soil maps, then quantile random forest to produce the maps. And what we mapped was soil organic carbon and soil texture. These are some of the results. You can see that the R square is quite low for SOC. For the texture is little bit better, but yes, it's 0.5. But in any case, you will see at the end that this went not so good, finally, in the simulation. And then we used this just derived by data that we didn't produce, but ERA 5 data for temperature. And so you see here which is the impact. So substituting the different remote sensing data to the simulation, basically, generally speaking, there is some kind of shift. For some of this substitution, you are almost in line with the simulation 0, but for some other substitution, there is kind of shift from the simulation 0. But I don't want to enter to all the detail of this simulation, which are at the end quite similar, each one to the other. So the impact of the different substitution is similar. But just to go to the final show or the result of the sensitivity analysis, in which it is clear that there are some boundary conditions which do not affect in a sensitive way to the final result. For example, I want to show you that climate, substituting climate, so not using in situ data for climate, but remote sensing, was not affecting so much. The same for above ground biomass derived by remote sensing was quite good. Instead, you can see that using these soil property maps, that also you have seen that the R square were quite bad of the maps, effectively produce great error also in the sensitivity analysis. So at the end, I can say that it is important when you use some kind of non-in situ data in your MRV system, it's important to use, to ensure that you are using some remote sensing data that it is good. So it's important to use, to have accuracy in these maps. So, for example, we could try to improve the map for soil properties, and let's see if this run better, for example. But in this, with this map that we produce, it's quite clear that they would, if you want to apply, I mean, this system to the landscape, you would have much more error in this case. And this was my last slide. I hope you enjoyed.
Thank you very much, Maria. We'll have that call.
Thank you very much, Eric Sechier, I have a quick question. So what you have modeled now are absolute trends in soil carbon, but in the context of the CRCF, what would be quantified is the delta between two simulations, a reference scenario and a baseline reference and a scenario with the carbon farming practices. What would be then the impact of having a inaccurate initial carbon stock on the modeling? With some models, I'm sure, like MJ, I know that there is no effect at all on the delta between the two modeling. So even if you are wrong on the initial carbon stock, it doesn't affect in any way the delta stock assessment. Would it be the same for you? Because that's what would matter for the CRCF. For other purposes, it's important to have absolute trend, but for CRCF, what matters is the delta between the two simulations.
Yeah, I mean, actually, I don't think that this is quite different, because we could have, now we have measured the different practices separately, or you can also model the delta. Personally, me as a scientist, I always prefer to model the real data, not the delta. I think it's scientifically more sound, I would say. But you can also produce the delta of these two simulations. So actually, I don't understand really which is the point here. So.
Well, it's because CRCF, in the methodology, you have to simulate baseline, and then you have to simulate, so with former practices, and then you have to do the simulation of what would change in terms of carbon stock based on new practices. And with the RODC...
Actually, what we have done, because as you have seen, that we have simulated the baseline, which is the condition of when you, as a farmer, apply conventional tillage and monoculture or...
yeah. What I mean is the error the same on the simulation with the conventional and with the carbon farming practices? Because with the RODC, it should affect the simulation in the same way or very similar, meaning that the delta would not be affected at all. And with a linear soil model, that's how it should work. So meaning that if you are wrong on the initial carbon stock, if you are using a soil grid products, etc., that wouldn't affect at all your delta stock assessment.
Yes, but this reinforced my idea that if you don't use the data, but you use the simulation separately, you can see if you have a difference in the accuracy simulating the conventional or the carbon farming. If you model directly the delta, you cannot find out where is the error, I think.
A little bit of a response, both of you. I mean, Eric have disagreed about this before, but I think the question is, how do we think of delta? Because if we only think of delta, that we have litter fall that comes into the system and it's inputted into the system, and then it starts decomposing in the system. So if we only think of delta as the addition of carbon because we did changes just that affects the litter fall, then the initial state should not affect that unless you're close to saturation point, unless you're close to some system where you say like, well, we cannot have anymore in this carbon system. Yeah. But if we think of delta because we are in a changing climate. If we think of delta as like, well, what's the total change of the amount of carbon in the soil? If we have a warming climate, it should also affect the existing carbon in the soil, and at which point what matters is not so much, like, of course it matters how much it is there, but it also affects the matter that, like, in what type of form they are there and how much of it is being released. So if the delta is just so it's the question of what do we think of as delta? Is it just the input, at which point you're going to say a separate, or is it the total, at which point you...
Yeah, I mean, I'm reflecting a lot of time on this topic, so I get to the conclusion that you cannot only measure what happened in carbon farming fields. You need all the time to have what we call in science the treatment, the basic treatment. So to compare to a condition in which you don't have the change. So in this way, you can, if you have a delta, and we have seen this. So due to the climate change, there is an intrinsic delta. But we have this because we have the conventional. So the conventional is the reference. All the other delta is given by the practice. Yeah, yeah, it's the same place, same climate, and yeah, so. But the other question is more difficult because you need to see the error of the modeling. So this is something more complicated. But again, I think that it is better to consider separately. Otherwise, you do not know where the error comes from. Yeah.
On the scientific point of view, I completely agree with you, but it's not what is demanded by the CRCF. CRCF demands a delta between two simulations. So that's why my question was really specific to the CRCF context.
Okay.
Maybe we can continue during the discussion time. I believe that we said at the beginning that we wanted to answer specific research questions to understand how we can design an MRV approach that is robust, transparent, and cost-effective. And as part of this cost-effective analysis, we are just testing which would be the best covariates, let's say, to have in mind. And I believe that part of the presentation of Maria was to identify key remote sensing approaches as well for soil organic carbon, the accuracy of this input data, and the time frame that we are considering for climate, if we can say climate, when maybe we should talk about weather streams. So let's continue during the discussion time. And now I would like to pass the floor to Gret to continue with the MARVIC results.
Yes, thank you very much. So we will keep this for the questions. Okay. So yes, let's continue also with some results from the MARVIC projects. Obviously, it was MARVIC and MRV were funded under the same call, so there's a lot of similarities, and that's also nice occasions like here to interact and to share experiences. So the MARVIC project was designed actually to develop this framework to develop context-specific MRV systems. And why context-specific, we believed? So we didn't think of developing a European-wide MRV system, but we thought it was very important to do it context-specific. And the reason was, of course, that there is a huge variability across Europe regarding pedoclimatic conditions, farming conditions, but also local legislation, for instance. So we try to grasp this and to see what impact does it have on the choices made for MRV. Another thing that we also think is very important is to make it scalable. So let's say that it should be cost effective, and it should also we should be able actually to cover a large area without a lot of administrative burden for farmers. We actually focus on 4 major land uses / soil types. So we focus on arable land, on grasslands, on agroforestry and woody crops, those 3 on mineral soils, and also on managed peatlands. We are a consortium of 16 partners across 12 countries. As said, actually, the main goal of this project is to make this MRV framework. And for that, we look at the different components of an MRV system. So we look at the rules and guiding principles. We have been thinking about issues like additionality and baselines and so on, but also the building blocks for the quantification. So on the one hand, we have data both for MRV development. So think already about benchmark size, for instance, for the calibration, validation of models, but also the data for upscaling. So data regarding to remote sensing, the farm data, the maps available, etc. And then, of course, also the models, because we mainly look into a measure modeling approach. So, and then, yeah, also to take into account is, of course, the user preferences, costs, but also policy coherence. And with all this, so we try to assemble this MRV framework for guidance for people who want to develop this context-specific MRV systems. And we also try to test this in the different countries, actually. So in we call them test cases. Okay, that's been... during the course of the project, I must say I've very much appreciated already, like also the interaction we have with the policy, because for me it's very exciting that at the same time of this project, also the policy is developing. So we really enjoy the interactions we have. There have been interactions with DG Klima, also with MRV for SOC together, the JRC, etc. So that is really very interesting. So that's why we also have published some policy recommendations. But today's session, I must say, we will focus mostly on the modeling component. So in the modeling components, we are working on a model catalog, on evaluation of models and making improvements. Also to connect the data and the modeling approaches into these operational processing chains. And of course, uncertainty analysis is an important factor of that. So Lisa Kulmala from FMI will first present the overall approach and also some insights from the test cases of Finland and France. And then Marta Berzola from Italy, she will give us an insight, a very comprehensive insight, I must say, from an MRV system they have developed for their Italian test case. So we focus on, we focus on the models. But we're also engaged in other sessions, also with MRV for SOC, for instance. We have tomorrow a session on data. So that's, we will present their metadata catalog, but also the work we have been doing on the role of benchmark sites for MRV development and also of farm data. And also today we already have had a very interesting session on sampling and uncertainty. Also tomorrow, so you have to choose, there is an interesting session together with MRV for SOC, also more on policy instruments on the socio-economical side. So also warm welcome to that. So that have been the contributions from the MARVIC project and to the Carbon Farming Summit. To give the floor to Lisa. So these are the contributors. So maybe if you want to discuss further on different components, many people are here. So I guess that will give a good chance to further debate about different aspects. So Lisa, I would like to give you the floor now.
Okay, thank you very much. Very good to be here. So my name is Lisa Kulmala. I come from Finnish Met Institute. And today, indeed, I'm going to give a general overview what we're doing with the models and modeling frameworks in MARVIC. Yeah. Great, thank you. All right, so my topic today is advancing operational monitoring approaches in MARVIC. I just introduce first what we mean with these monitoring frameworks and what is the MARVIC approaches. Then, as Gred introduced, there will be a couple of examples about testing of these systems and applications in the end. So, okay, at this hour, you of course know why we are all doing this. So I will not, I will skip most of the motivation, but I just want to highlight the difference. What is the difference between a model and this, what we call an operational processing chain? In Orcasa, where Erik was active, they call this same thing scalable quantification platform. So the difference, so model is a model, everybody knows what that is, but these operational processing chains, they include also the data streams, all the pipelines, all the filtering, gap filling, harmonizing those. Then there's of course these models with calibration, validation, and there's a full IT system with maybe some APIs and of course handling error situation, what to do when data is missing, and servers and disk spaces. So that's the difference between model and this operational processing chain. So this is a bit busy figure. This was created in Orcasa project, and we are building on that. So Orcasa project concentrated on arable lands, and in MARVIC we have these different land use soil types, as Craig introduced just in a minute ago. So in addition to arable, we're doing also peatlands, agroforestry, and grasslands. And what I want to highlight here is this middle part. So this is the whole MRV system, but what I'm talking now is this monitoring methods. So the models that we are using, or the approaches that we are using, there are three different categories. There are so first of all, we're using mainly these tier 3 approaches. So there's process-based modeling. So the first one is soil-centered approach. So there's some kind of litter input, maybe from statistics or somewhere, and then there's a soil model like ROTC or AMG or YAS or something like that. Then there's the models with the strong coupling between the above ground or the vegetation and the soil. These are usually called ecosystem models. You know, there's a feedback from soil to the plants and so on. So those are strongly coupled. And then there are these light coupled approaches. Erik calls those parsimonious methods, where you have a plant model which usually introduces litter to the soil, and then the soil model runs there alone. And you can have these approaches with or without assimilating of data or data assimilation. Usually, of course, Earth observations are assimilated, but those can be also like soil carbon observations and so on. So in MARVIC, we have 8 teams who are building and testing these operational processing chains. So we have Agro Solutions, we at FMI, ILVO, INRAE, Chagask, Università Cattolica from Italy, Andreas here, Wageningen, and SAE, SAE. And they have various approaches. Many have these parsimonious, but there are also ecosystem approaches, soil-centered approaches, and we think that is a very good and advantage for us that we have those different approaches. What is common? Typical data needs in all of those. So there we have soil organic carbon, either from maps, this like Lucas or some other product, observation, Earth observation data, usually Sentinel-2 is used, or Landsat. Then, of course, weather drivers, those can be ERA5 or some local product or even observations, and then, of course, farm activity data, which can also be statistics or then from the farm management system. So what we have utilized in MARVIC in model testing or this approach testing is, we have multiple data sets, but one key thing is this, or key data is this crop 2021 data set that is collected by Erik and his team. So it consists of 14 European crop cropland edicovariance sites located in Central Europe and then a little bit southern and northern. But it's not just the typical flux site data set, but there is it's a very rich data set, including not only like the fluxes processed in standard ways, but also the vegetation. There is biomass samples and also Earth observation derived estimate, for example, for leaf area index. There is soil data like soil carbon stocks are of course very useful, but also texture, hydrological properties, and what is also very crucial is this management. What is the carbon input and output at the yearly basis, or even on a shorter interval. And together it's 163 site years with 16 different crop species spanning from 2001 and 2022. And we have done testing with that. This is just a short example from our Finnish or FMI MRV system. So we have two different modeling approaches that we're testing. So on the right-hand side, we have this CARBS model, which is a parsimonious, pretty lightweighted model or approach. You utilize Earth observations like Sentinel-2 and then radiation intensity, then some weather drivers, and then the soil organic carbon pool. And of course, the carbon input and output. And what we have here in this figure, the topmost panels are the photosynthetic inputs, cross-primary production, many know GPP. Then the second one is the respiration, total ecosystem respiration, which is the autotrophic respiration and also the decomposition of soil organic matter. And what we have here on the lowest panel is the net exchange with atmosphere. So what we're missing here is the input and output by farmers, so these lateral fluxes, but flows of carbon. But what we can see that this very simple method, CARBS, does pretty decent job, even though it was calibrated in Finland and then utilized in this independent data set. Then the other one, the SPICY, is an ecosystem model with a lot of hydrological features, taking more into account all kind of stomatal actions and soil water. And well, there are maybe some more developmental needs there. But this is example from Carbon EU. So they have also tested the model with edicovariance data. What we have here in this panel is the net ecosystem exchange that is observed, and here is the simulated one. But what is also important is that there are these different carbon pools and carbon fluxes that we can compare. What is here is the biomass of wheat at these flux sites. So this is above ground biomass observed, and here is simulated, so it's doing a pretty decent job on a plot scale. And here is on a pixel scale on two different fields. So what we have on the left-hand side is the simulated yield, and here is the observation of that. And again, here is the simulation and observation. So what was already raised in the previous, there is a field internal variation which should be encountered. And they have also, Erik and his team, tested these different biomass data sets. What we have here is first is a biomass of wheat in France, second is a biomass of maize in France, then it's cover crops in France, and the last one is tomato in Italy. And again, on the x-axis there's the observed, and on y-axis there's the simulated. So we can utilize these different pools and fluxes for model testing. This is the previous presentation was about this long-term experience. Just to remind that we are also utilizing these long-term experiments, such as this one in MARVIC, but more about those maybe later. Now we move on to the application side. So the first application example is from Finland. This is a farm with chicken, and what we have here is the farmer has maybe 20 fields. I selected few for this picture. So each single panel is one field, and these bars are single year, and you can find the years here on the bottom, and what we have on the y-axis is the photosynthetic uptake, GPP. And the different colors indicate different cultivated species. So if I remember right, this one is oat, then comes wheat, barley, pea, and this one must be the autumn wheat or winter wheat. So you can see that there is a rotation. This green one is that it's more or less grassland all the time. But it's just the GPP. I just wanted to show it because what you can see here is that if we look at this winter wheats, so at two different fields at the same year, the one, the photosynthetic uptake was much better on this plot compared to this field, even though it was the same yield and same species, highlighting the need for field-specific monitoring. But when we get to the full carbon balance, this is again a bit busy, but I'll walk through this. So what we have here is, again, these boxes are individual fields. So we have altogether 12 fields here, with all having 6 years of simulations. And now the dot here means that indicates the net ecosystem exchange. So it's the sum of all this atmospheric exchange. And if it's negative, that means that it has been a sink of carbon. And if it's positive, it means that it has been a source of atmospheric carbon. And then in this bar, we have taken into account these lateral fluxes, so the carbon that the farmer has taken out of the field, which is yield, of course, and then there is also some organic input, because you remember it was a chicken farmer, so there's some manure to be put. So if here, these are the grasslands that the farmer wasn't actively cultivating, so that's why the and now this is just to be sure. Now this negative bar means that it has been a sink of carbon. So it's a negative delta SOC. So sorry about that. But so it has been a sink of carbon, and positive values means that it has been a source of carbon when we take all of these fluxes into account. So here at the grassland size, mainly the carbon balance is the net ecosystem exchange, because there's very little of this lateral fluxes. In some cases, there might have been even input without output, and that's why the carbon change is, or carbon pool change is even more than just the net ecosystem exchange. But in many cases, when we take these lateral fluxes into account, the plots turn into a source of atmospheric carbon. So they are losing carbon. But that's, you might wonder, what are these red ones here? So those are the fields, or when the farmer utilized cover crops. So when we analyzed how much was the average carbon input of these cover crop fields, we got into this type of a figure, which is average over the whole farm. So this blue line is the current practice, that like business as usual, what the farmer was doing. And if he, so you see, in general, the fields were losing carbon, but if he wouldn't have used cover crops at all, those would have lost carbon even faster and will lose carbon. But then we made also this what if scenario. So if he would always use cover crops when possible, let's say like with spring weeds, with all plants, that's of course not possible, but then this would have been the case. Okay, now to the second and my last application is from France. So this is a little bit different scale. Eric and his team has simulated the whole France, but you see it starts from the pixel level, then to the parcel, then to the region, and then to the whole country level, national level. And they have also made similar analysis on a regional level that what if there would have been a cover crop or what is the impact of cover crop in these farming systems. And now this is my final slide about the next steps. So we are currently working on this cost accuracy thing. So we all know that we need to be accurate enough, we need to be robust enough, but we should also be cheap. So we are checking what is the role of internal conditions, drivers, mainly weather, model parameters and management. So if we use very costly data streams and if we use very cheap data streams, how do those propagate in the final outcome? Maybe other things to mention that we're also working with this uncertainty thing in general and working with this methodological framework, combining data and models. But that was my presentation. Thank you very much.
Thank you, Lisa. Maybe time for one question or so? If not immediately, then I will give the floor to Marta, who will present us a case study from an area in North Italy. But it's always difficult for me to pronounce the name, so I won't do that. No, also the region.
Emilia-Romagna. Yeah, I know there is a GN, which is difficult for non-Italian speakers. So good afternoon, everyone. I'm Marta Beltoa. I'm from Università Cattolica del Sacro Cuore. And I'll tell you, my main goal of this afternoon is to do not bother you too much. But of course, my second goal is to present the result from our study, where we have evaluated if regenerative practices implemented for the industrial tomato supply chain can generate verifiable carbon removal by using a hybrid MRV methodology. So the industrial tomato supply chain offer, I would say, great opportunities to test carbon farming solution because it is one of the most intensive agricultural systems. It requires a lot of input for water, fertilizer. The soil is often compacted due to heavy machinery traffic, and tomato produce relatively low crop residues compared to cereal, often within a narrow crop rotation. So the plant carbon input is limited and the soil are often carbon deficient. So in this context, we have tried to answer to two main questions. The first one is if regenerative practices implemented for this system can effectively increase the soil organic carbon stock compared to a baseline. And if they do, can this carbon removal be certified under the CRCF regulation? And to answer this question, we have applied a hybrid MRV methodology that we have called remote-C that combine field measurement with modeling and remote sensing to simulate soil organic carbon dynamics. This tier 3 approach is also coupled with a tier 1 approach, which is called the Cool Farm tool, that allow us to simulate also agricultural soil emission and greenhouse gases associated emission. The remote-C approach was presented yesterday by our colleague Michele Croci, which he proposed its further implementation for the upscaling of this approach at the scale of a carbon farming project. But today I will present its the raw form, its first implementation for the farm scale. So it is basically based on the ROT-C model, on a modified version of the ROT-C model, where the exogenous organic matter, like carbon-rich crop residues or organic amendment, can follow different decomposition dynamics than the fresh plant carbon input. The model is initialized with soil samples that are selected with a smart soil sampling, we have selected for this study the conditional Latin hypercube sampling that enable us to capture the variability of the soil. And the initialization of the model followed 3 steps, which is the spin up with around 500 years of forest, followed by a spin down following baseline management for around 100 years, and a warm up with 5 years of the usual baseline for a specific baseline. The plant carbon input is then calculated from the estimated crop biomass with a light use efficiency model, in which the biomass, or better, the net primary productivity, is estimated from the photosynthetically active radiation that derive from the analysis of the satellite-based crop indices. So our study was located in the Piacenza province in northern Italy, where we have applied a paired comparison, where 15 hectares were managed under regenerative practices, and the other 15 hectares follow a baseline management. And this allows us to have an activity-specific and dynamic baseline. Oh, sorry. So in these fields, we have applied a 3-year crop rotation consisting of wheat, maize, and tomato. Under the carbon farming activity scenarios, wheat straws and maize stubbles were incorporated together with a balanced addition of nutrients with biodigestate in order to foster the humification efficiency. We also applied during winter cover crops and managed the soil with minimum tillage. And all these practices were selected with the main goal to increasing plant carbon input and those carbon removals, despite we have considered yet practices that explicitly reduce the agricultural soil emission. So the field measurement demonstrate that under the activity scenarios, thanks to the implementation of regenerative practices, we have increased the soil organic carbon stock of more than 4 tons of carbon per hectare over the 3 years, while we have continued to lose carbon under the baseline management of around 0.5 tons of carbon over the same period. The remote C approach was able to follow the soil organic carbon trends, producing a comparable increase and loss of carbon in the activity and baseline scenario, respectively. This was translated in relatively high model performances if we consider the absolute soil organic carbon stock over the 3 years monitoring period. But of course, since the CRCF requires us to validate the model under the delta SOC, as it was also pointed out previously, as we expected, thanks to the limited number of data and the short-term monitoring, the modeling performance was lower. But importantly, the mean model bias remained below the pool and mean uncertainty, which is a key requirement from the CRCF, which means that we didn't introduce a systematic bias, so we didn't over or underestimate the soil organic carbon stock. But beyond the bias, the CRCF requires also a specific precision of the estimate. This means that 90% of the observations shall fall within the 90% of prediction interval. And in our case, also this requirement was met, since only the 10% of observation fallen outside the prediction interval. So with this simulated data, we have started to calculate the temporary net carbon removal benefit and the net soil emission reduction benefit, following the formula proposed by the CRCF. I will present them as average between the lead commercial farm, without going into detail for each farm. So with the remote C approach, we have on average estimated carbon removal in the activity that were set to 0 in the baseline, while we have, on the contrary, LULUCF soil emission under the baseline that were instead set to 0 in the activity. And with the confirm tool, we have estimated a reduction in agricultural soil emission thanks to the adoption of the cover crops for almost 8-9 months during winter, thus reducing the nitrogen losses that we usually have leaving the soil there. However, under the activity scenario, we had an increase of greenhouse gases associated emission due to mainly additional operation for managing crop residues and cover crops. So these components were used for the calculation of the 2 units, where the greenhouse gases associated emission were subtracted by applying a weighting factor. So at the end, we obtain almost 20 tons of CO2 equivalents in the 3 years per hectare. But to this unit, we have applied an uncertainty deduction factor that we have calculated following the Verra protocol that allow, or at least propose, an analytical procedure that was suitable in our case for this small-scale study. And with this analytical calculation, we were able to explicitly quantify the model error and the sampling error. So with this method, we obtain around just 26% of uncertainty deduction factor, which is high. It is related mainly to a model error, but is quite good for us because the model wasn't locally calibrated and validated, so leaving us some space to improve or reduce the uncertainty deduction factor once the model is calibrated and validated for our region. So by applying this factor, we have reduced the total units for CO2 per hectare in the 3 years. For the CRCF, these carbon removal are already considered temporary and subject to a reversal risk. I know that you have already seen this picture this afternoon. It was presented by Panos Panagos. So this risk of reversal is required by the CRCF to be taken into account ex ante. So we also apply this risk index on our, using our data from the baseline. That allows that we have a low risk of reversal since most of the soil were far from the saturation. But despite this, we have simulated with ROTC, we have extended the simulation over 60 years, assuming that the practices are continuously applied for only 3 years, and then the practices are reverted back to the baseline. Or also, we have hypothesized a continuous adoption of these practices for over 10 years, and then again, the baseline was adopted. But our simulation tells us that the sequestered carbon do not remain for over 1 year after the activity ended in most of the cases. But not to ensure, but to test the credibility of these generated certificates, we have quantified the climate benefits related to both carbon removal and soil emission reduction. So together with our colleagues from Agroscope, we have calculated the cooling effect by using the cumulative radiating forcing, by using the FAIR model. And if we consider a representative farm between the 5, we see that the carbon removal in both cases have a continuous cooling effect. But when the carbon is released in the atmosphere, as in the case of the 3-year activity, we have a warming effect after only 20 years. But importantly, or not, it's important to note that N2O, the reduction of N2O emission that are represented in orange have at the beginning a relatively small cooling effect, but that increase in importance toward the end of the simulation, highlighting its irreversible and immediate benefits on climate, also because the N2O have significantly higher cooling warming effect than the CO2. Those suggesting us that agricultural practices that specifically aim to reduce N2O emission could provide more climate benefits. But despite the climate benefits, and this is the last slide, but not least, beyond the increase of soil organic carbon, the adoption of these regenerative practices provided also soil-related co-benefits that in this short term were reflected in an increase on nitrogen availability and microbial biomass. And importantly, also, we did not face a significant reduction in the yield, thus avoiding the carbon leakage in this potential project. So thank you, everyone. I know that I said many things in 10 minutes. But I will be happy to answer to your question.
Oh, questions. Yeah.
Thank you. Thank you for the presentation. It was very clear and full of details. I'm new to this sector, so I have a very basic question. You mentioned the sea saturation, which I think is the maximum loading capacity of a certain soil of carbon. Is this?
It is calculated based on our measurement and what the GRC proposed as the maximum capacity of the soil. It is a comparison.
Okay, but the maximum capacity of the soil that is suggested by the, let's say, regulation is the same for all the soils, or it's a sort of theoretical value?
It's not theoretical. It's based on the mineral associated organic matter. We know that certain soil that have that are rich in clay and silt.
Okay.
Are more able to,
so based on the texture,
to store more carbon. It's based to the soil texture.
Okay.
Also.
Okay. So then another very short question, because the subject is very interesting. You mentioned you mentioned this let's say carbon content that has been measured directly and modeled at the same time through the simulation models. And at the end, you mentioned the issue of permanence of this carbon, because I saw that you consider a different kind of carbon source, cover crops on one hand, and compost or digestate on the other hand. So the quality of the organic matter is quite different. I mean, typically cover crops, green manuring, sometimes, most of the times, that kind of carbon is not to stay. It can stay, but for a very, very short time. It's another thing with respect to a composted carbon that can stay longer. So I wonder if your model is considering the quality of the organic matter that you are considering to incorporate into the soil in terms of, in light of its permanence in the soil. Wake up. Okay, I don't know if I was clear enough in my question.
It is actually, I said before, that is a modified version of the ROTC model. because it is able to integrate separately the decomposition dynamic of the exogenous organic matter that follow different decomposition dynamic based on a work done on incubation experiment that tested the degradation of both crop residues, carbon-rich crop residues, but also different organic amendments. And also for the cover crops, we have followed a suggestion from our study that proposed different decomposition, like coefficient of decomposition for the green, the plant that is incorporated already green and not senescent.
Okay, thanks. Maria, I saw you also had a burning question.
No, because it's related to what we do, so I'm interested to understand. Because you have mentioned that you have used for biomass input in ROTC, the FR, so NDVI. Did you also have measure biomass, so input from the crops?
Yes, every crops.
So did you
it
also
started actually as more an agronomic work that then moved further integrating also the modeling part, but we have measured the crop biomass.
So did you also did as we did some kind of calibration of this remote sensing?
It was the light use efficiency model was cross-validated with our data for this case. But then my colleagues are working on a larger scale, calibrating and validating then the model using data from a larger scale. And yeah.
Being coordinator of development of remote C, yes, we did it. Both for ROTC and the light use efficiency model, we have applied a Bayesian calibration. So we did a sensitivity analysis. We identified the different parameters to parameterize. And basically for all the crops of the Emilia-Romagna region, we ran the validation on many of 2,000 sites where we have the commercial yields. And I can tell you that on average, a root mean square error of less than 1 tons per trimatter per hectare for most of the major crops have been achieved. But the most interesting part of this work that everything was automatized from remote sensing. So it means that the carbon removal can be really generated without many farm management activity data, because also thanks to the work that we are doing with CNR, we are detecting also all the practices. So that you don't have the needs to go around sending technicians and agronomists to get the farmer activity data. So if the permanence of residues is detected from satellites, you don't have to go there to check. You don't have to check if it's right or not, the declaration if they are cultivating, cover crops.
But do you think that if you have calibrated one time, you could apply even if you don't have more data for your crops in the following year, so you can continue to apply a same calibration you did, for example, now during this project? And yeah.
Because when you have a posteriori distribution of your parameter, you are able to generate as agricarbon AO, as Eric is doing. We're doing basically the same things. You can generate every time, at every pixel, the uncertainty related. So you can propagate the error even from SOC measurement, from above ground dry by measurements, because you have calibrated. So you have a posteriori distribution of harvest index or many of the parameters. So of course, if new data comes in from the supply chain, it's perfectly. In fact, it is also allowed by the CRCF inside cross-validation. But the fact that if you do not propagate the error using a Bayesian, you are stuck. You need to have analytical measurement to say every time how accurate you are.
And just to tell you, these are all the steps further beyond this study. This is the easiest implementation of remote C that was applied on a farm scale. Then for each component that you see for the remote C, we are testing and implementing it on a larger scale, at least at the province of Piacenza, and then in some cases for all the region.
Okay, I can see it's about time. I don't know, Marta, if you still wanted to have an overall discussion or we leave it for the break. Yes. So yeah, I would like to thank you all actually for attending. Yes, thank you to the presenters. And I'm sure if there is more questions that, we will all be happy to discuss further. So have a nice poster session and networking again.